So I don't know, I don't have a lecture really. I don't have a PowerPoint or something, so I'll be jumping back and forth between maybe the HTML that looks nice and running some of the code in the Markdown. And yeah, feel free to interrupt me if you have any questions along the way, and maybe everyone else can keep an eye on if you see any hands pop up or questions in the chat. Yeah, so the topic here is generically model evaluation and selection, and I think I'll be repeating some of the lessons learned or presented in the other talks from yesterday and today. But I'm using sort of a generic example with synthetic data. So maybe that'll help to, first of all, make the problem a little bit more manageable, so you can actually see the data and see how it's looking. And we also know what the what the true underlying relationship is in this data, and we'll see how well we can do in finding that with some of the approaches that I outline. Yeah, unfortunately, it's lots of packages. Some of them are used for only very small components, but I think you've installed several of these already for the other tutorials. The ones that are probably new are GA, which is a genetic algorithm, forecasting, which I'm going to use just to generate some data. This one called MEMOIS, which is related to the genetic algorithm that I'll be showing. So anyway, hopefully they're all on CRAN, so I hope it's not too difficult to install any of them. Okay, so the general introduction. We're going to focus on some examples for strategies for selecting statistical models for use in management strategy evaluation. And just general, you probably already know this, but some of the criteria that we want to consider when we're choosing our models, as has been mentioned already several times, is we want it to make biological sense. So hypothesis-driven models, I think, is a key underlying criteria for choosing models. Not that we get some great model, but it makes no biological sense and we don't know how to explain it in a paper. So that's one of the criteria that we've tried to follow. And you don't necessarily need to know the precise mechanism in all cases, but they have to be somehow plausible, I think. Secondly, we want a model that fits the observed data well, but with the caveat that we don't want to overfit the data. So we'll see some approaches in identifying when we've overfit data, and how that looks like. And we also, with specific reference to MSE, we want models that can make good predictions into the future. And specifically, we're also going to be comparing whether our model is better than some sort of simpler, naive model in order to adapt it for prediction. Okay, so moving on, the first section here is just describing how I'm creating the data. So what I'm going to be doing is a stock recruitment relationship. And here we have a few different models that, well, one variant of a Ricker model that was described in these papers. I think this is similar to what Isabella was showing. So up above here we have the standard Ricker. And then in log space, if you turn it around, it becomes this nice linear model where you have your response variable, you've got an intercept term, you have a term that's just the SSB, the spawning stock biomass, and then you have one with a coefficient fit to SSB. And this specific relationship that was described in these papers called the controlling type, there's many others that they listed as well, But this just adds this extra term here that has some sort of environmental covariate and an additional coefficient here. So that's just adding another term. It's still quite easy. And then I just wanted to point out, this is this Levy paper. I think Isabella also referred to it. So there was lots of different models that they looked at. They've got a Cushing, a Ricker, and a Beverton-Holt. And then they have the ones that were modified to include some environmental covariate. In some cases, this is just an additional term. Like this one, this is the one that we're going to be using, this modified Ricker. But they also have other variants of it where it might be interacting with SSB and so forth. But for the purposes of this example, I've chose this very simple Ricker, and we'll use that going forward. Okay, so first I'm going to define a bunch of environmental covariates. And I just am using this autoregressive integrated moving average model from the forecast package to do that. Here we have, I'm going to generate 70 years of data. I'm going to generate 12 covariates, and I'm just choosing randomly what's going to be their degree of auto correlation. And what then, yeah, maybe one additional change I did as well is to add some trends to 2 of these 12 covariates. So on X01 and X02, I have this additional long-term trend in the data. And so here's what's coming out. We have our 12 covariates to varying degrees of autocorrelation. The ones that have a higher autocorrelation, you see these longer lagged processes, oscillations through time. And then the low degrees of autocorrelation, you have quite a noisy pattern that's changing from year to year. And these first 2 covariates at the top here are the ones with the trend added to it. Okay, so next step was creating the biological covariates. Was there a question? No. Okay, so what I've done here for the spawning stock biomass, I've just used a random walk process, and I've used our environmentally mediated Ricker to generate the recruitment values. I've selected 2 of the covariates to be significant modifiers to the recruitment, or mediators to the recruitment. And then on top of that, I added some additional noise, which was a log normal with a 20% coefficient of variation. Yeah, so this is the random walk on SSB. Then I just made up basically my values, which were taking this Ricker relationship and adding on these 2 environmental covariates at the end. And finally, this is the additional log normal noise. And so we get this type of data that's generated. So quite a meandering SSB and the recruitment, and you get this typical shotgun-like shape of stock recruitment information. Looks like there's some sort of trend here, which is good. We know that there is a true relationship under this, but there's a lot of information going into that through the 2 covariates and this additional noise. And then again, looking at the covariate or the correlation plot of all of these, we have the covariates X1 to 12, and then the SSB and the recruitment. So you can already see here that we have some positive correlation between SSB and recruitment. But there's also some other spurious correlations that are popping up. We have one with X11, which is not a true mediator. And then we have several up here that seem to be having higher correlations. X1, which does have a mediation. X2 is not there. X3 is a little bit lower, but that's actually one of our covariates, and so on. So hopefully the idea was that we made this somewhat challenging problem for us to dive into. Okay. So what one often does, and you saw this in the example from Molly, is maybe starting off with the most complex model that you could maybe imagine, all the covariates that you wanted to test, and then slowly reducing that model to some simpler, more significant relationship. So in this example here, I've started off by including all of these covariates. It's got the offset SSB or log SSB. So there's not going to be any coefficient related with this. What's not shown here is an intercept. So that's our log alpha intercept that's part of the Ricker. That's just by default going to be in the equation. Then we have SSB as another covariate, and all of the environmental ones after that. So that's what I'm doing then is fitting a GLM, generalized linear model. Nothing fancy, but what is a little bit different is that I have this log link function on here, and that's a typical relationship that you might have for a covariate or for a response variable like this, where you're only predicting positive values. So the underlying assumption, and Molly, you correct me if I say anything stupid statistically, is that the error distribution in log space is more normal than in the original untransformed space. And this will also limit the model from predicting anything, any negative recruitment values as well. Okay, so once we have that, you have probably done something similar, even with a linear model. You can call a summary, and it's already giving us our covariates. It's showing information about the relative statistical significance of some of these terms if you were to drop single terms. So some of these are coming out to be highly significant, like the intercept term, which we didn't see in the equation, but it's there, the SSB. And then we're having some that are popping up like X12, which was not one of our covariates. X3 is just on the border of maybe being significant at this P05 level. X1, which is another one that's truly in the model, is not popping out yet. But anyway, you start to get some idea about which covariates might be more important than others. And this could already be a place where you could start removing terms by hand, looking at the ones that are least significant, perhaps, and working backwards until you get to some minimal model where everything is significant. Also, what's produced here is the ICE, which we'll come back to later. Okay, so to do that by hand with so many covariates can be a challenge. And what's an important concept to remember is we want to look for the best model, and whether these additional terms in the model improve the predictive power. So the more complex model you have, you're always going to be probably improving the R squared of the fit to the response variable, but that doesn't mean it's going to be necessarily a good model to predict data that it hasn't seen before. And thus comes the problem of overfitting. You can have a model that looks great on paper, but once you take into account the complexity of the model and the number of coefficients that you've fit to it, it can quickly break down. And so we're going to be using, among other metrics, the ICES information criterion for the first example. There are different variants of this, like the BEIC and the AICC, which Molly presented earlier regarding, or I think is especially applicable to models with low sample size. But in any case, the AIC penalizes these very complex models with the term K here, which is the number of estimated parameters. And what's a common strategy for finding more simple models is to compare nested models. So you compare a model with maybe all the terms, drop a term, and see whether or not there's an improvement in the AIC. You can even use the ANOVA function to compare nested models like that. And yeah, as a general rule, none of this model doesn't have it, but you may have that in your work, where if you have interaction terms, a general rule is you want to start by removing those before you remove any of the main terms. There's a little bit of a discussion about if that's always applicable, but that's sort of a general strategy. So you would only remove the interaction between x1 and x2. Sorry, you would only remove x1 and x2 if you've already removed their interaction first. And this is the logic that's used in the automated stepwise search routine found in the function step. By default, it's using this backward search, where it's only going to be removing terms, and it's always going to be selecting the most the largest improvement in AIC to remove these terms. But you can also have the direction be something more complex, like both. This allows basically the terms to come back in at a later stage. And I think unless you have a huge model, that's usually a nice setting to have, so you don't accidentally throw out things that might become significant in the smaller model. Okay, what's also important for this setting up is the step function includes the ability to specify the simplest model with this lower argument. So down below here, I've basically defined what the formula should look like for the simplest Ricker formula without any environmental covariates. So it's not going to remove SSB or the offset or the intercept. That's always going to stay in the model no matter what. And as long as we define that, and we've defined the upper, which is the sort of the starting model, which is using all of the covariates, then it should work backwards. And this is quite fast. If you want to look at what's happening during each of the steps, you can have this set to true. And then maybe I'll do that just so you can see what it looks like. And you can see it runs fairly quickly through all of these models. The way to read this is at this current step, it had thrown out lots of covariates, and it's still got 1, 2, 3, 7, 9, 11, and 12. And this is the current AIC for that model. And it starts going through, and it's removing 7, it's removing 2, it's removing 9, etc., and looking to see if we can get a lower AIC. And there's several here that do that by throwing out 7 and 2. And it looks like by throwing out 7, there was the largest reduction in AIC. So that then becomes the next model, and the term X7 is no longer in the model. And it keeps doing this. You can see in the next step, this is a it's a both direction search. Some of these terms might come back in with this plus sign, and some are dropped. And after several runs, it arrives at this model here that still has 5 environmental covariates. And then I've just printed out the summary of that model. Now notice that even though this model has the lowest AIC that was found by the algorithm, it's still got a few covariates here that are on the border of being significant. So these have a p-value of 0.1 in this case. The algorithm is just trying to minimize AIC, and it's not using any other significance criteria to get rid of terms. So that's something to take account of. And then this is the end AIC. So if I look at the resulting comparison between our full model and the one that results, we have decreased AIC quite substantially. And of course, the R squared has gone down, but only minimally in this case. So it did get rid of a lot of junk. Yeah, and note that a general rule of thumb for significant improvements, so let's say this P 0.05 level, is generally that your change in AIC should be bigger than around 2, your delta AIC. And so we saw in that example that, oops, where am I? Okay, so in this last step, we went from, well, let me take the step before. We went from 1540 to 1539. It was sort of on the border of this rule of thumb. Okay, any questions about that so far? Okay, and the other option, if your model fitting is relatively fast and there's not too many possible combinations. So in this case, the number of possible models is 2 to the n being 12 covariates minus 1. So that is, did I spit it out here? I have 4,000 possible models, but these are quite quick to fit. So dredging is actually not a big issue in this case. And I'm not even using this parallelized version of dredging that I think Molly may have used in her example.
From what I read, I think p-dredge might be outdated, and now they're including the dredging, the parallel ability in the regular dredge function. So I just used the main function. Yeah.
Good. Yeah, but it's fairly similar to the stepwise, but we're going to be able to try all the combinations now. And the only thing that's different is we define a fixed argument, so terms that always have to be in the model. I'm defining as the offset, log SSB and SSB. That's our default Ricker, but otherwise it's going to test all possible combinations. And just to give you a feel for how long that takes, I think it's less than 5 seconds or something. It's really fast in this case. Although now that I'm running teams in parallel, it may not be the same. And you can turn on this tracing to true, but I think it's almost too much information to make sense of. I discovered that there's this plot in addition to the summary table that Molly showed you that shows you which covariates are in the different models. So the best model, the lowest AIC, is this top row, and it includes the intercept, SSB, as do all of them. It also includes X1, X3. Those are both true covariates that we wanted, but it also includes 11 and 12. And in fact, several of the the leading models have this X12 inside of it, even though they have 1 and 3, it's picking up this this other covariate there that shouldn't be in the model. It's just noise. Okay. So now we have this simpler model, which I guess I've kept temp at this point, or fit. But in any case, you may want to, at this point, visualize what your model is doing, especially if you have interaction effects. It can be difficult to really understand what all the coefficients mean for the ultimate response of the model. So what we've done a lot in SEAwise in looking at these more complex models, especially the growth ones, is to look at the marginal effects. And basically what this is doing is it's holding all other covariates constant. What I mean by that is the environmental covariates, and just looking at the effects from a single environmental covariate at a time. So in the following example, what I'm basically doing is looking at which environmental variables were kept and just choosing one that's going to be my focus for the plot, and finding out what were the historical quantiles for that focus variable, from the 5% quantile to the 95 and a few in between. And for all of the other environmental covariates that are still in the model, I'm just looking at their median value and using that. And so this is what's basically coming out. I generate all possible combinations of SSB along the observed values and just varying that X01 covariate and looking at how that affected the model. So in this case, you can see it's affecting not only the maximum value, but also the steepness at the origin. So that's what that controlling type is doing. There's still a lot of residual noise, but maybe if you squint your eyes a little bit, you can see that a lot of these darker color, let's say it's temperature, a lot of the lower temperature values are down below, and a lot of the greenish teal colors are up above. So it makes sense that this gradient is coming out of the model. Okay, so that was the sort of historical way that we do a lot of model selection. If you have the time and if prediction is specifically of interest to you, like it is for us in an MSE type simulation and forecasting into the future, then it's sometimes helpful to do cross-validation. And this is basically, it's a very flexible framework. It can be used to compare models of different structure as well, depending on the metric that you choose to highlight performance. And it basically splits the data into two sets. We have a training data set, which is used to fit the model. And then we have a holdout one that we use for prediction. This is the validation set. And it can be used as the basis for selecting best performing models, or this could be whether or not to include a term or whether or not to use a certain structure or not. And under careful design, cross-validation can identify models that suffer from overfitting through decreased prediction performance. So it can not only find a model for you, but also in a way, like AIC, it can penalize for being overfit, hopefully through decreased prediction performance. And the performance can be evaluated based on whatever desired metric you choose. And this could be even several metrics. So let's say you want it to be a mixture of root mean squared error and maybe some envelope of values that is deemed acceptable for the outcome. You can basically design it as you want. So it differs a little bit from AIC in that it's more general and it's data driven, and it directly estimates predictive performance on new data. It's also applicable to both parametric and non-parametric models. On the other hand, AIC is faster, it's theory-driven, and it penalizes complexity based on the number of parameters, but it doesn't have this implicit aspect of prediction inside of it. I honestly don't have a good idea about which are the best metrics for every situation. I've listed a few more common metrics here and tried to generalize when they might be more or less appropriate. So the one that you choose might differ from those by the model fitting criteria, which is also interesting. And I've seen some reference to that being sometimes a benefit, like let's say the model is fit in log space, but you're still interested in the absolute values of the prediction. That's where you could use maybe a different metric than's used for the actual model fitting. To start off, squared error metrics like mean squared error or root mean squared error will more heavily penalize outliers and large errors. Another quite common one is the mean absolute error, which is quite intuitive because it gives the average error in the same units as the data. Mean absolute percentage error and mean absolute scaled error provide scale independent metrics, and they're useful when data varies significantly in magnitude. And again, one may further decide to calculate these metrics based on log transform data, but that doesn't seem to be as common as I thought it was. So here's some metric functions that I've just provided for you. They're very simple. In most cases, it's taking your observed response variable and the estimated one and just calculating the metric. So mean squared error, RMSE, mean absolute percentage error. There's a median version of that. And then this last one's a little bit different. This we'll see at the end of the talk. This is the mean absolute scaled error. And what's different about this is it has this third argument here for a naive prediction that you compare to. So you've got your observed response variable, you've got what you predict with your selected model, and you've got, let's say, the next best prediction from a naive model. And basically all this is it's a ratio of this previous function. So it's the MAE of your model over the MAE of the naive prediction model. And what you're shooting for is a value lower than 1 in this case. Something that's better than the naive. Okay, so now we move to some practical examples for cross-validation. The first flavor, what I'm calling flavors, because there's many different ones, and it depends a little bit on the the strategy that you're interested in, what are the properties of the fitted model that you're going for. But one that's very common is called a k-fold cross-validation. And in this case, I'm going to be just doing a slight variant of that, which is a repeated k-fold cross-validation that we run several times for a bit more of a robust output. So in this example, the k signifies the number of random groupings, which we're going to call folds, to use for the training and validation data. The groups are balanced such that each data sample will be used once on the validation side. So it'll be used for k-1 fittings, and it'll be used once as a validation set. And for example, the commonly used 5-fold cross-validation will divide the data into 5 groups, where 4 out of the 5 are used for training. So training the model and defining the covariates that we're going to use. And the other 20% is used for the prediction of the model. And as I mentioned before, to increase the robustness, we repeat it a number of times. So the first step here is to give you a few required functions. I realize I probably reinvented the wheel a little bit here. Bernard was pointing me to a package called Covariate. I think that's how you pronounce it, which has a lot of cross-validation functions already built into it. And it seems quite a good package. But in any case, for our purposes, I think it's nice to see that it's not rocket science. It's quite a simple function to set something like this up. So the k-fold function is just going to randomly split our data into the number of folds that we want. And the cross-validation function is going to refit a model to each of the folds that are spit out from this function and observe the predicted response values. So there's an inner loop that's doing that, and there's an outer loop that's just doing it a repeated number of times. What's also important is when you're comparing the cross-validation performance of 2 different models, you always want to use the same seed so that they're both using the same partitions of the data for the k-fold designation. So this is the first function here. You define the number of folds that you want, and it basically just splits the data into gives an index basically for every row of your data frame, and says which rows will correspond to which fold. And for the next function, it takes a model input. So this is the model that I want to refit to each of the folds. And I first get the response variable out of it. I'm getting the formula out of it. And then this outer loop is for each permutation. So each repeated k-fold, I'm doing this outer loop. And once it gets into the inner loop, it's dividing up the data into either training or validation data sets. It refits the model to this training data set and uses the same formula, of course. And then it predicts the result of this updated fit using the validation data and spits out the response variable. And that's it. So in theory, or in praxis, what's happening is, let's say I divide my data from this example into 5 folds. Here they're just randomly assigned such that each value is put into one of the folds, and they're roughly of similar size. And so that's random in terms of time, and this is what it looks like in terms of the yeah, the stock recruitment data. This is just an example of what the model would have fit to. In the case of fold 1, all of these red points are held out for validation. It fits the model to all of the remaining points, so the orange, the blue, the green, and the purple. And then it looks at how well it's able to predict the values of the new set. If you give it the SSB from the red values, what is the prediction there? Okay, so before we go further, I just wanted to comment on the choice of the number of folds, which is kind of important. You usually will choose the number of folds depending on several considerations, such as the variation in the data, the number of samples, and the computation cost. So you can imagine if you have a high number of folds, let's say we use 30 folds. We're only holding out maybe 2 data points in each fold. You have to fit the model 30 times, and the computational cost can be a lot. A low K, such as 5, is just 5 model fittings, and it usually provides a good balance for the types of models that we've looked at in our project. So the larger amount of validation also provides a robust measure of prediction error. And the low computation, or the low number of folds, is not computationally costly. And I would say that using a 10-fold or a 5-fold is pretty standard strategy that seems to work well in a lot of situations. There is a special case of cross-validation called the leave one out, in which the number of folds basically equals the number of data points. So you're only leaving out one data value for each run of the model. This of course takes a long time to do, but you don't have to repeat it. Every repetition of that is going to be exactly the same. What's interesting about it is that it's going to be least biased in terms of the error that's coming out. So the amount of error that you're predicting from cross-validation is not necessarily a true error. It might, yeah, depending on the number of folds you do. You've basically given more or less data to the model that it sees when it's fitting, and the larger the amount of data that you hold out, the less, yeah, the more error is probably going to be involved in that. So in this following example, before we come back to the stock recruitment example, I've just shown you basically what the choice of fold has on the error. Just a simple linear model here, 20 points. And so 20 is going to be the maximum number of folds. This is the leave one out cross-validation. And I've just repeated it several times and looked at the RMSE coming out. And if we look at the generated data, so I had this relationship going in. I've got just 20 values. I'm prescribing values for the intercept and the slope, and then I'm adding this error on top of it. So I know what the magnitude of the true error is in this data set. And since I know that, I'm able to then state what is the true RMSE of the error. I have the error that's coming out of the fitting of the linear model just by itself without any cross-validation. And you can see that it's actually below the true error. And finally, we have the values that are coming out of the cross-validation. So inside of this, this range of values, we're I think, 50 permutations. So I ran the cross-validation 50 times, and I only was varying the number of folds in each one. And so you can see that the bias in this error slowly approaches the true error of the data set. And it's the model error that's usually slightly more optimistic because it's actually seen all of the data in its fitting. It's not necessarily overfit, but it's seen every data point, and this is typically what's going to happen, is that the error is going to be slightly lower than reality. So cross-validation not only provided a less biased estimate of the error, but you can also see how it approaches the true error as you increase the number of folds. Okay. I think this is probably a bad example. I don't know if Molly's still here. But in any case, sometimes when you are fitting models of different structure, you cannot compare their AIC directly. So I'm not sure if it's the case in this GLMM TMB, but in some mixed models, you might get a drastically different AIC than a similar linear model due to the addition of these random terms in the model. However, using cross-validation, you can choose whatever metric you want to use to compare the performance of the models. And so it has that additional advantage. So what I've done here is I have my two models. The first one is the one with all of the variables in it, and the other one is the one that I think just had 5 of the covariates left over. I'm basically applying it to this cross-validation function. It's a 5-fold, and I'm repeating it 5 times. So I have those two cross-validations to begin with. And then I have this other model here, which is, I'm just going to refit the smaller model that we got out of the step function. And I'm adding an autoregressive term here to the time. So this should have made it a mixed model, but I was actually surprised that the AIC values were not that far different from the other ones. In any case, this takes a little bit to run, and I did not choose what the metric was going to be that I would use as the ultimate decider of the best model. I'm spitting out several different ones, and I've used this strategy in the past where I look at a model across several different metrics and sort of decide on the winner based on some overall best performance. So here are the resulting statistics coming out of the full model, of that smaller model, and of the mixed model. And I'm calculating all of these 5 metrics, pasting them together, and this is what comes out. So in all cases, the smaller model was better than the full model. We knew that already from AIC, but here we see it in all of these other metrics as well. And the mixed model, the addition of this autoregressive term did not improve the model. So that would be a very strong indication to choose this model of the 3. It's not only better in terms of AIC between these two that we could compare, but it's also better in terms of all of these metrics. Okay. So now we get to a bit more complicated example. This is the using a automated model selection with machine learning. I don't know how common this problem will be for you all, but in the case of the work that Bernard has done, and using a lot of these principal components from very different environmental fields, we ended up with a lot of potential covariates that were chosen, in this case, 82 different principal components. They were based on what we thought were potential biological mechanisms for the recruitment of North Sea cod. And they were time series signals extracted from environmental fields at different time periods. So this was different seasons or a yearly average or different lag values. So there ended up being quite a lot. In fact, there were so many that we had, and I had to look this number up. This is 4.84 septillion possible models, and that's without any interactions of any of these covariates. So basically a brute force approach is going to be impossible here, but also even a stepwise approach could be extremely time consuming. Yeah, when you factor in the cross-validation and all this other steps. Now, he used a much more sophisticated genetic algorithm than I'm going to show you here today. But just so you know that if you have one of these problems, this is kind of state of the art. You might be interested in looking at it. And is it also in Marmalade an example, Bernard? The NSTA?
Yeah.
Yeah, so I'm going to show a simpler version of this. We have 4,000 models to choose from here, but you'll see that it's when you add on top of it the cross-validation, it's going to take longer than what we had in the previous dredge and step functions. So cross-validation is great, but if you want to do it correctly, it's going to definitely add some computational time. And so some of these search routines that are a bit more sophisticated can be really helpful. And basically what this genetic algorithm requires is a fitness function. So I'll explain a little bit more what it's doing later. But the fitness function is just it's going to take basically a guess about the coefficients or the coefficients to include that are provided as a binomial vector. And so it's going to be zeros and ones basically as to whether or not to include a given covariate. So it's going to be, if it's 0, it's not included. If it's a 1, it's included. And the output of this fitness function for the purpose of the genetic algorithm is just a single fitness value that it's going to use to decide whether or not certain solutions will be kept for the next generation. And in the fitness function that I have here, I'm doing a repeated k-fold cross-validation. And the fitness is going to be just a single value of mean absolute percent error across all of the data points. And yeah, so depending on how many permutations I have, you're going to have several estimates for each row. Yeah, later on, I'll be interested in the variability between those permutations. You can turn this to false to get a little bit more information, but when it's true and it's default, it's just going to spit out that single value as the output. And I'm going to start off by giving it a bunch of simple models as starting configurations. So I have 30 individuals, so 30 possible functions or 30 possible configurations for the model to begin with. And I'm going to start off by just including all of the single term models, so just X1 or just X2 and so on. And then I have the rest of the 30 individuals. I'm just going to make random combinations of 2 term models. So this is what comes out. It's just kind of a first guess. And with these types of searches, it's good to start simple and let the algorithm explore more complicated models as it goes along. So the first 12 individuals are just turning on one of these covariates at a time, and then the rest are randomly assigned. So we have individual number 13 has the 4th covariate and the 10th and so on. And just to visualize what the starting fitness of all these combinations look like, I have this graph here. So in this case, we want to technically minimize mean absolute percent error, but for the purposes of fitness, it's going to try to maximize whatever it is. So you just have to multiply this by a negative value in our fitness function to make sure that it's trying to maximize that value. And so this is the starting population, and you can already see that X01 is one of the better models that seems to be popping out. But there's also some other ones, like the combination of 1 and 9, 4 and 12, and then there's a mix of lesser performing. Okay, maybe I'll just show one more step of this script, and maybe we can take a 10-minute break so I can get something to drink. So now we're getting to the genetic algorithm. So we're going to use this GA package, and there's a nice vignette there if you're interested in looking at it in more detail. But how they generically describe these genetic algorithms is that they're stochastic search algorithms inspired by the basic principles of biological evolution and natural selection. They simulate evolution of living organisms where the fittest individuals dominate over the weaker ones by mimicking the biological mechanisms of evolution, such as selection, crossover, and mutation. So what's going to happen is, based on the fitness, it'll decide which individuals go to the next generation, and it'll mix up their genes according to some of these settings. So we have a P crossover, which is how those parents are going to mix their genes and what frequency and probability they're going to mix their genes. There's the possibility of a mutation, so a gene couldn't just spontaneously come on or off, depending on that probability. And there's a few other settings there too. And just to note, this is a very specific case for term selection in a model, but you can also use these algorithms to fit coefficients, like a continuous value as well as this binary one. And finally, we've arrived at the script. Before we run it, just wanted to show you, I have one little thing that's less typical. That's this extra diagnostic function that's going to be basically recording the fitness of every individual evaluated. If you don't do this, you'll get just the end population after the algorithm has been run. But I'm interested in looking at sort of the spread of solutions across model complexity. So that's all that's doing. And also in this step, we are converting our fitness function into a memoized version. And all this is basically doing is R is going to remember, okay, have I tried the combination of including X2 and 11 before? And if it has, and it knows the outcoming fitness, it won't even run the cross-validation. It knows what that result is going to be. And so you're able to save yourself some computation time if you have one of these binary type searches to do. So maybe I will run this in the background. It's not printing. You can also, so some of the other settings that I have here are, so I've passed the population size. I've given it the suggestions as our starting population. These are sort of typical settings for the P crossover and P mutation. I've put a little bit higher. Elitism is how many best performing individuals will automatically be carried over to the next generation. And I'm not running it in parallel. I'm going to run it for a maximum number of 100 generations. And if I don't improve fitness for 40 generations in a row, it'll stop earlier. And otherwise, it's pretty much, I think, self-explanatory. The only thing I wanted to change here was true to monitor what's going on so you can see what it looks like. Hopefully it works. It is really slower. So it's hard to see here, but it's printing out in each of the best fitness and the mean fitness of the whole population. It starts off kind of slow, but now you see it speeding up because it keeps hitting these combinations of coefficients that it's already evaluated. So that's this memoization aspect coming into effect. And now it's finished after about 41 generations. So you can see here in this figure, it found the best performing model after just 2 generations. We know it's a relatively simple model, so it found it quickly. And the population gradually got better over time until it sort of peaked out. Okay, so now we'll look at the results. One of the plots that we found helpful to look at the outcomes of these is to plot the complexity versus fitness. And since we're using this, since we have all of the individuals that were evaluated through all the 40 generations, we have lots of combinations of models and lots of fitness values to investigate. What this next bit of code is going to do is it's going to calculate what's called a Pareto front. And maybe it's better to just look at it first. So this is what it looks like. We have the metric that we're using for fitness on the x-axis. So in this case, lower MAPE is a higher fitness. And then we have the fraction of the covariates that were included in that model. So the very bottom here, we have the one that didn't have any of the covariates. This was our lower limit for the model, the Ricker, and that was the MAPE associated with that. Then we go to the single covariate model, and we have the best performing here. and a bunch of poorer performing here. Some of them are better than the Ricker, but a lot of them are worse. And they're also colored by when they were evaluated in the evolution. So lighter color means that they came in basically earlier in the evolution, and darker was something at the end. The width of this bar is relating to the fitness, the range of fitnesses that we had for a given k-fold, which we ran many times, and the number of permutation was 10 times. So we had 10 values for mate, and this was roughly the range and the variability that we got in between permutations. This is the two parameter model, and it's slightly better in terms of performance. The same thing can be said for the next one, but at some point we start to say, this is actually the best model. And the reason we said that this one and not this one is because it lies basically to the left of the confidence interval for the previous simpler model. After that, we get a better fitness, but it still lies within sort of the distribution of values. So we stop there, and all of these three models represent the Pareto front. We have a 0, a 1, and a 2 coefficient model, and everything after that is considered poorer. You see, even for the higher complex models, you start to have really drastic overfitting, and this error starts to curl back to the right. So it's identifying both the best model and this overfitting issue as well. Okay, and this was the data that went into the Pareto front. We have, so the best performing one in terms of fitness was this first one, this first row. Actually, no, this is by model complexity. So the 0 coefficient model is on the top, and then these are the best models at each complexity. So for the one parameter model, it included only x01, and for the two parameter model, which was the best one, we had 01 and 03, which were the coefficients that were actually the true ones in this example. And then they get more and more complex. Yeah, there's just a little bit more information here on Pareto fronts. I must admit that it was hard to find sort of a general rule for deciding this absolute best model, and I wasn't finding a whole lot of information on the repeated k-fold situation. There is this one standard error rule if you're just doing a single k-fold. But when you're doing a repeated one, it wasn't so clear, at least what I was finding, how you choose it. In any case, this one is just lying slightly to the left of what this confidence band is showing. So it's sort of minimally better, but you could have maybe gone for the next simpler model. All right, so this was our best model that comes out of the example. We had a total of 1,230 fitness evaluations, and memoization evaluated only 163 unique models. So we saved about 87% on the computation time by using that option. And only 163 model configurations were tested out of a possible 4,000. If you let the model run longer, it would probably test even more than that, but it seemed to find basically the best model relatively quickly. And this other genetic algorithm that I mentioned that Bernard has used basically forces the genetic algorithm to always carry with it the best 0, 1, 2, 3 models along the Pareto front. And it seems to be a little bit better when you have highly complex combinations.
Can I say something about it?
Yeah.
Yeah, the one that I use is a multi-objective fitness function. So I'm optimizing the number of parameters and the mate, for example. And what Mark did here is only having the MAPE in the fitness function and guiding the algorithm. So by having like two objectives, you really constrain it towards this simpler parameter space.
Okay. Hopefully that was more or less clear. I don't know, again, if you're going to need such a tool for your work, but again, in our case, we had lots of covariates. The good thing about using principal components is that they are all orthogonal to each other. So those, even though there's a lot of covariates in that example, a lot of them are going to be completely uncorrelated. So that gets around some of the problems that Isabella was mentioning regarding collinearity between covariates. But it can still happen if you have multiple fields. Good. So now I will move into a few other flavors of cross-validation. This is sort of a huge topic, and you can really get lost in it. So it depends on, I think, what your objectives are, what kind of cross-validation you choose. The first alternate consideration I wanted to mention was called blocking. So until now, those k-folds were defined completely randomly. But it could be, if you have some sort of autocorrelation in your data, that you're going to want to design your holdout data a little bit more intelligently so that you're able to address that autocorrelation. You may get, if you don't do that, you may get overly optimistic predictions of your data because the neighboring values are going to help you predict. So in those cases, the folds should be defined at a scale that is larger than the residual autocorrelation in the model fit. So if we look at our response variable, we do have autocorrelation occurring in the recruitment time series, but as far as I understand, this is not the actual criteria that you want to use for determining if a blocking strategy should be used. It's rather what's left over after you fit your model. So this autocorrelation is largely explained by the covariates that are already considered, such as SSB. And what's left over then is barely coming across this significance line. So in our case, even with just the fitted Ricker without any environment on top of that, it looks like we don't have much of a problem of autocorrelation in the residuals. But if you did, you could have this blocking strategy where your folds are basically a certain amount of time, or in a spatial model, you'd have some squares of data that you leave out that are above the spatial scale of autocorrelation, and you would have these be holdouts through time. So this would be then, I've just defined a minimum block size of 6 years in this case, and then the algorithm or the function that I included in the example divides up the data as close to that minimum size as possible. So here we end up with 11 folds, and you would hold out then one at a time, fit the model, and predict the other fold. You can see here that there's actually a lot of similarity in the fitting of the models. But on the other hand, you do see some blocks of data, like these light blue ones that are all below the model line. You see other ones like the green ones that are all above. So there's something going on there, but because across all the folds, it's sort of, it gets washed out. I'm guessing that's why the autocorrelation was not deemed very significant in this case. Anyway, so that could be another consideration. Because because of the way that you set this up, you can't really repeat it over and over again. So this would be a single cross-validation that you'd be able to do with this blocking strategy. And the last flavor that I want to talk about, and this is getting back to, I think, things that were mentioned on the first day as maybe being of interest to some of you, is a hindcasting technique. When this is specifically important when you're looking to predict into the future. So the example that we've had until now, we did a repeated cross-validation. There was no real future that was held out. But in this case, if prediction performance is important, you may want to select validation data more carefully to prevent the model from seeing the future, which could potentially bias the results. It might make things look a bit more optimistic. So this strategy could be that you have a training set as before, but you have two different types of holdout information. You have a validation set, which is like our folds from before, but you have a second holdout, which is the testing holdout. So this might be the most recent data period. You're going to fit your model to everything but the most recent data and decide which model is the best for that training and validation period. And then you're going to measure its performance in predicting on data that it's never seen. In addition to addressing effects of autocorrelation, this setup may also test for prediction performance when the time series is non-stationary or subject to drift. There's a bit more detail here, but I think the main points that I want to mention here is even if you're having this kind of setup, you could still use this sort of general idea that you hold out between 10 and 20% for that validation step. And then the amount that you hold out for the testing set at the end could possibly be related to the forecast horizon that you're interested in. If you're interested in forecasting 3 years into the future or 10 years or something, that might inform how much data you want to leave out in that case. And finally, we come back to this maze metric, which we've used a lot in the project, which is to always make that comparison to the testing holdout comparable to some naive prediction. So you see whether or not you've really gained something in terms of predictive power over a simpler model. So here's an example of what the structure might be. In this case, we're using a large chunk of the historical data for training the model and only a smaller chunk here for validating it. So maybe this process would be used to select the model that you want to use for forecasting, the green and the red. And once you've decided which model performed the best on that fitting and validation set, you would then use that selected model to test your predictions on the last holdout. And in our example above, since we didn't have any strong autocorrelation detected, we could still use this k-fold strategy to select a model based on everything except the last 5 years, for example, and use the maze statistic to evaluate its prediction performance for the last data. So that's what I've done for this final example. I've just defined how many data points I'm going to hold out for the testing phase, and I divide the rest of the data up into the training and validation and the test data. I run the same model again on just the training and validation data set. Otherwise, I think it's exactly the same. And look at what comes out then on the Pareto front. And if you run this, it should be even a little bit quicker. And what comes out then is that two-parameter environmental coefficient model becomes of lower fitness than the single one, just from the removal of those last data years. We still make significant gains over the default RICR. So this has it's just got the X01 left in it, and our other covariate that's technically part of the relationship drops out. Either it had, the signal wasn't strong enough, or it was, maybe there was important information that was only in the final years, but in any case, it drops out. Okay, so now we've decided which model we're going to use for the testing, and that's what this next chunk is doing. I'm getting my naive prediction, which is the geometric mean of the last 10 years of the recruitment. So this is the last 10 years of the training and validation set. And I'm predicting the best model. Then I have the Maze statistic, which is calculated based on the observations for Y, the predictions for my best model, and the naive prediction. And just for comparison, I'm showing the Maze for the non-environmentally mediated RICR. And the rest is just setting up the plot. And this is what we get. We've got our data used for the training and validation in black. We've got the test holdout in light gray here. And we have our naive prediction, which is flat, of course. It's just a single value based on the geometric mean of the last 10 years. The prediction of the environmentally mediated RICR in blue, and the prediction of the RICR without X1 in green. And what we see here is that our maze is below the naive model, but just barely. So we're below 1 for our best model. But actually, it's the RICR without the environment that has the substantial improvement over the naive model, which is interesting. So I would think that a maze of this degree would be sort of not enough evidence to really go forward with that model for short-term predictions, whereas the RICR might be. Also note that the stock recruitment models were given the correct future SSB and environmental conditions. Even 5 years into the future is quite a stretch. So that's another thing you have to, I think, consider when evaluating the maze of a given prediction is, have we incorporated the true uncertainty and the other covariates that are feeding into that? So this is probably overly optimistic in this case. And finally, I wanted to sort of tie this into some developments in the assessment world that are moving towards being a bit more objective about how they view the predictive power of their assessment models. And I wanted to show one of the strategies has been to look at the importance of more recent data in making predictions. So, and I hope these concepts are related. They're sort of two sides of the same coin. What I'm going to be doing here is basically removing the most recent data 1 year at a time. And these are known as peels. And I'm going to be doing this to basically get rid of that most recent data, refit the model, and see how much variability there is in the reconstructed prediction of the historical data. But then I'm also going to use that refitted model to predict into the future. So you've got two things going on. You've got how much variation in the model fit is due to those most recent data points. And that's called a retrospective analysis. If you have sort of the model is always shifting in one direction, that's a sign that those recent data are sort of biasing your perspective of the model. And that's been typically done for a lot of stock assessment models. They'll do these peels, fit it to one less data year, and run it again, and see how the predicted models lie on top of each other. But then I'm taking these refit models and I'm also predicting into the future. I'm just doing it for a single year in this case. But therefore we get from the historical refitting, we get this metric called Monroe, which is this retrospective bias metric. And then I'm using the maze to look at the predicted variability. I won't go through the code in detail. It's not very complicated, but it's just chopping off data points, refitting the stock recruitment relationship. Again, this is the model with just X1 in it. And here I have a zoom of the last 5, 6, 7 years of data. So you can see when as I peel away these last data points, without any peeling, we have this red line. That's the fit to the full data series. Then I get rid of a data point and fit it again. And there we have the yellow line, which is starting here. And the yellow point is what's predicted with that model. Do one more peel, we're in the green one, and so on. And you can see here that the historical reconstruction of recruitment, it's all the same model, but there is some variability going on. According to this statistic, though, it's not overly biased. So this would pass sort of the threshold that's defined for a lot of stock assessment models. I can't remember exactly what it is, 0.2, I think. And then the maze is showing basically how well these single year forecasts were doing with the model fit to those different. And I think it was Diego that was talking about incorporating environmental covariates into an assessment model. I think a strategy like this might be a way to tackle that. If it's not AIC or something else, you could see if adding these environmental covariates improves your model, both for the fitting data, but that you also pass these other tests in terms of retrospective bias and the ability to forecast in the future. That might be a criteria for keeping that. Good, then I just have a few concluding remarks, and that being that during the SEAwise project, we had similar results to this synthetic example on the predictive power of environmentally mediated models that for us illustrated these important considerations and trade-offs for using them in MSE. The first is that their use in the management procedure. So let's say you want to look at if you get better performance from your harvest control rule or management, if you make projections about future recruitment, for example, using environmental conditions, that this doesn't seem to be something that's going to happen very often. And we actually see that in a lot of the work in ICES. I think there's only been 1 or 2 cases where they decided to predict future recruitment based on current environmental conditions, and they were quickly burned the next year by getting it quite wrong. And I think our results are showing similar results, that on a short-term forecasting, we're not seeing huge gains from using those models, but they nevertheless could be identifying true mechanisms on the long term. And so their use in the operating model, such as part of describing biological dynamics, can provide important tests to the robustness of a given management procedure over the long term. Yeah, so this ability of a given harvest control rule to produce favorable outcomes across several alternate but likely operating models provides additional confidence in the management procedure. And I would leave it at that. We don't have a whole lot of time, but if there's questions. Molly.
I wanted to comment that I didn't get to it, but if you were trying to forecast the length and weight like I was doing, then you would have to do it iteratively, where you predict from one year to the next.
Yeah.
Because the length in 1 year is a predictor required for the length in the next year. And so it's a more difficult procedure. And I think that maybe some of these methods wouldn't automatically work. You might have to, I looked into some of these packages, like the forecast package, and some of the cross-validation automated methods. And I was thinking that because we have to do it iteratively, it gets a little more complicated. And do you have an idea of which ones might work for forecasting growth and cross-validating it, like the K-fold stuff, or do we have to write it ourselves like we did in the actual research project?
I think the main thing that I've learned primarily from Bernard is the importance of model selection with this data that's not seen by the model yet. So as long as the period of forecasting that you want to do is held out from that testing set, I think that's the most important consideration, so that you don't bias how good your predictions actually are. But yeah, I think that's the idea, maybe to do in hindcasting of stock assessment models as well, because they would be able to feed back. The recruits become the 1-year-olds, and then you could actually progress your forecast over several years rather than just the single one that I've done here.
Yeah,
I don't know if that answers it completely. Yeah, but it's sort of the deeper I looked into cross-validation, I saw so many different flavors of it. There's rolling windows like we did. There's all sorts of strategies for the way that you hold out data. So yeah, hopefully it's a simple example, but it'll depend on the given problem a little bit.
Yeah.
Matteo.
Yeah, I just want to add, I completely agree. And but the INCAS also is not only good always to see the sensitivity of the prediction, but in my opinion, also to see the trend of our model. In this case, in this particular case that you show, Mark, you see that the model seems to overestimate, because all the points are upon the main line, the pillar 0, let's say. So also in this case, it can be helpful to see if which are the direction of our model for the prediction.
Yeah.
And I have a technical question still sometimes about the performance metric for the INCAST.
For which metric?
The performance metrics of the INCAST, the MASE one, I never understand which are the threshold. If there's a threshold, just we look at the lowest value and just say, okay, this is the lowest value that we get. So it's probably the best model, because I never understand it.
Yeah, the threshold is basically a value of 1. So if you have a value of 1, then your model is doing exactly as well as the naive. So you want to be at a value lower than 1. And yeah, the further away, the better. Yeah.
Okay. Thank you.
Yeah.
Oh, I wanted to comment on the naive model using the geometric mean recruitment for the past 10 years. We do that in our forecast to be conservative, but I'm guessing it wouldn't always be the best predictor because the arithmetic mean would probably be it's usually gonna give you a more accurate prediction. But in this case, the recruitment had been quite high for the recent time series, and so getting the geometric mean to bring it down a bit is a better fit.
Yeah. I guess it's probably close to a median value, right? A geometric mean.
I don't know. I haven't heard that sort of thing.
Okay. Yeah, it's so that's pretty standard, I think, for a lot of stocks. The good thing about it is even if you don't know what the environmental mechanism is that's possibly driving recruitment changes over time, if you're only focusing on the last period, you're sort of implicitly stating that you think you're gonna be in a certain regime that's similar to the recent past, rather than taking the geometric mean over the whole period. But I guess it depends on how fluctuating your SSB has been in that time period as well.
Mm-hmm.